Hello,
So, hello.
hello. Am I audible?
Yeah, you're audible.
Hello. Yeah. Thank you. So, Sayed, so you are registered for this course? Like
Yeah, I'm
going to
registered for
give
multi.
exam? Uh,
Sorry,
you are going to give that the exam like for the certification, or you are just trying to learn the subject?
trying to learn the subject as of now. I've not registered for the exam yet.
Okay, okay. So from where you are, like which college or
Uh,
currently you are preparing for?
yeah, currently I am first year PhD student at IIT Delhi.
Oh, IT Delhi.
Okay.
Okay, so maybe you will be working around this microfluidic stuff. And
Yes, that's why I wanted to learn on about this.
okay, good then. Actually, these tutorial sessions are meant for like we are told to discuss questions which are more or less directly related to the stuffs that are taught by the instructor in the class in that particular week. And at the same time, we have to make sure that like uh, after going through these tutorials you will feel somewhat comfortable with the uh, the assignments that are being given for that particular week that will be anyway evaluated at the end. So I will be somewhat looking at the I have looked at the assignments and I have chose some of the questions which are not that much tough, and at the same time it is related to the content that sir has taught in this particular week. And I will be meanwhile connecting the questions that I have took with the content that sir has taught. So this will be a bit, like it will be somewhat recap of the lecture that sir has taught, and at the same time, somewhat new expansion of the concepts that sir has told. Like in the lecture, sir has given somewhat explanation about the velocity profile in the channel flows. So how that velocity profile will be parabolic or those stuffs I will be taking up here. So in
Okay.
between any questions that you will be having or any further clarification about the course that you want me to explain, you are free to ask or interrupt in between. And
Okay. This will be for the week one, right?
yeah, this will be for the week one, and the content that is here, it is entirely related to the week one. Somewhat basic fluid mechanics will also be coming up into the picture, but more or less it is week one content only. So
Okay.
this will be a very basic, as if as it's like uh, some people are very comfortable with the subject. Maybe some PhD students are watching it, and at the same time, some of the bachelor's students are also joined or registered to the course. So things will be here at the moderate level, not very
Okay.
rigorous.
This subject is also new to me.
Oh, it is new to you. Okay.
Yeah.
So, like, I will be starting now. I
Fine.
have taken some of the questions which are related to the course content, and at the same time, I will be solving those in this particular page. Let me change the color of this page. So, so uh, meanwhile, I will be going to the sir's course stuff, whatever sir is teaching. So this will be kind of linked to the course content. So these are the slides that sir is teaching. Am I right? Like first
Not
week one content sir has taught. I mean, wait. Uh, they have given me this. Yes, Young's modulus and this flow regimes, different flow
Yeah.
regimes he has
Yes.
taught.
Yes. Yes.
Yes. So that's all. So like first question that is there, like which of the following flow regime is observed in the vertical channel flow. So only you are there or some more students came up. So like this Yeah. So so my slides have not shared, I think. Now the screen is visible.
Yes, it's visible now.
That time I think I thought I have shared it. Yes. So uh, which of the following flow regime is observed in the vertical channel flow? So so you try solving. Then meanwhile I will be looking at somewhat related stuff, and then you may go through the lecture slide that you or notes that you have taken.
Okay, okay.
So like in entire week, no, they used to there will be three lectures or four lectures in some courses, and then it's like the recap or revision of the students through the small quizzes based on those content that sir is teaching.
Okay.
So which of
So
the following flow regime is observed in the vertical channel? So it's like not a single choice question. Here more
yeah,
than one option can be correct.
because stratified flow will not be there. That only occurs in the horizontal channel that Sir has taught, and only slug flow, bubbly flow, and I think this dispersed bubbly flow. Yeah, three options will be there for the first question.
Okay, so you mean this like this bubbly flow is there, and then this
Only
is
the
visible.
stratified flow will not be there. That's the B option will not be there. Rest
So what is
everything
the
will be
reason for
there.
that? Can
A,
you
C, and
just
D.
what is the reason for that? Like what the term stratification means?
Hello.
Uh, hello, hello, am I audible? Wait,
Uh,
hello,
I'm not able to hear you.
wait. I'm again. Hello, am I audible? You just join again, if possible. You lost the connection. Wait, I have to reconnect it. Some technical glitches there, so I will connect it. Yes, so I have to reconnect the Firefox. Mm, please. Why it is not connecting?
Hello.
Hello. Now
Uh,
my screen is visible.
Screen is not visible yet, but camera is visible. I mean,
Wait,
screen. I mean, the video call is visible.
wait. Actually, this internet issue is there. I think.
Okay.
Wait, I will be again sharing the screen.
Okay, sir.
Yes. Now this should be visible.
Yes, yes, sir. So, what is the difference between this bubbly flow and dispersed bubbly flow? I mean, I'm not getting exactly what it is.
So just in terms of the
Size.
like in dispersed bubbly flow, the droplet or that miniaturization will be there in terms if it's like air is there. So that gas bubbles will be very small in size. So these are like flow different flow structures. So the names are given as per the uh,
Structure, size, and structure.
yes,
Okay.
yeah. So in the dispersed bubbly, there will be more miniaturized, and there is like intentionally dispersed also, in which these bubbles will be further miniaturized. So miniaturized means the length scale or the size or diameter of the droplet is getting uh, smaller and smaller. So my screen is visible, okay?
Yes, sir.
Yeah. And this, okay. So another thing is like can that stratification I was talking about. So what is that stratified flow means?
Like layer by layer, the fluid is liquid is flowing. I
Means
mean, in horizontal section channel as showed in the slide.
okay.
Like
So like this is the channel, suppose. Okay,
uh,
and the no, not this. The channel could be drawn much better. Wait. Like for example, this channel is there, and
mm,
something like this is happening. Okay, so
mm,
one fluid is coming from this direction and another from this. Suppose silicon oil is coming from silicon oil is a very highly viscosity oil. It is coming from the front end, and benzene is coming from the second end. So benzene is like transparent water like liquid. Okay, so it is coming up, and these two fluids which is coming into the microfluidic channel. Suppose this microfluidic channel is having its dimension around 300 or 400 micrometer. Okay, so you
okay.
see, so in this benzene and the silicon oil, when these will be mixed together in a beaker, say
Mm-hmm.
in a glass. Okay, so when you put both together here, they will be anyway miscible with each other. It's like sugar and water mixed
Okay.
together. But when these two fluids will be inside the microfluidic channel, they won't mix. Rather, they will be in their own layer. For example, benzene is coming from here, so benzene will be going like this, and silicon oil will be coming up here. So there will be one layer. Suppose this layer is this layer, this marked layer is shaded layer is for silicon, and this another layer is for benzene. So they will not mix.
It will depend on the flow rate also, no?
It will depend on the flow rate, but whatsoever flow rate you take, there will be very less chances of miscibility among each other. Because there is one question also in the lecture only I have taken. I will be showing you that question. Then we will be connecting that question along with the stratification that we are talking about. So, for example, this question number, uh, yes, this one I think, yeah. So, question number 24, you see why mixing is an issue in a microfluidic channel.
Okay.
So why mixing is an issue in the microfluidic channel? In the search lecture also, somewhere when you look at, so some in the lecture you see somewhere are told that in microfluidic channel mixing is an issue. So why is that so?
Like this case only because even if, as you mentioned, because of different flow rates, even if we pass the
Yeah, yes.
we are not
Essentially,
getting.
essentially the flow is laminar in this miniaturized
Mm.
channel. Okay. So this, if the
Viscous
flow is,
effect is more.
suppose this I am showing you. This video is visible, na?
Yes.
Yes. So the application slide is there. Okay.
Yes, yes, it's
So so
visible.
so 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 see, if water and oil is there in a channel, you see, then what
Mm.
will happen? Suppose oil is the central one and water is from the both sides. So this will be creating this kind of droplets of oil. Okay, this can be reversed also, but you see, it is in the case of oil and water, there is oil and water is anyway not miscible with each other.
Mm-hmm.
So they are anyway immiscible inside the channel also. But the problem is, you see the last one, this particular thing, you see here the black line is there and this white line is there.
Yes.
This one, if you see, uh, this is the situation. So uh, I will be showing it up. You see this, the flow is happening, two fluids are coming up but they are not mixing. This is an example of silicon oil and the benzene. And when how we are going to mix them in the microfluidic channel if required. As we told that it is very difficult to mix in the microfluidic channel. So what is the solution for this? So people have employed electric field. So this these black things are electrodes. So they have employed here, and through that they have mixed it. You see this undisturbed interface is getting undulated after passing through this black end. Uh,
So I mean, the inlet of this benzene and silicon oil is the same as you showed the
yeah,
T-shaped channel.
that is exactly the same. Just in this microscope image, only the section where it is crossing electrode is shown.
Okay,
Essentially,
okay.
from this side, benzene is coming, from the straight oil is coming, and these both are coming into the microfluidic channel. They are not mixing with each other, but once you applied for the electric field, it started mixing. But you see, when you increase the voltage, then mixing is much severe.
The- Oh, okay, okay, yeah.
So this particular question I took just because it doesn't make some more sense when it is spoken in the class. So now it will be much senseful to you, like what is
Yes.
actually happening, physically happening into the channel. So the take home message is, if two fluids are miscible with each other in the macroscopic domain, maybe they will be immiscible with each other when they are uh, pushed through the microfluidic channel. So it is necessary, sometimes it is required to mix them into the microfluidic channel. So people are employing different force fields, for example electric field in this case that I have shown.
Mm.
Sometimes people have also employed magnetic field too, in order to just mix the fluid on demand wherever it is required. So this is true for our body also, like when a child is very small, or like very newborn child, or lots of nerves are there inside the body, and this nerves are some nerves are in the range of micron. So in that our blood is flowing, and blood is anyway containing lots of components along with that, like cells are there. So like there, this mixing is necessary in terms of nutrient transport and those things. so
Mm.
so or sometimes like some drugs that are pushed through the veins are creating this kind of scenario. So in that case, if mixing is required in any case in the microfluidic channel, so that can be employed. So does it make sense to you? So like stratification terms is a broad term that can be used in different context. For example, you see this is the one we were talking about. Okay, so here
Yes.
we see there is uh, there is different kind of stratification. First is like viscosity stratification, viscosity stratification. Sometimes it is like density stratification. So like for example, in this sea, if two fluids were will be there, okay, then for this particular layer, the density will be for the benzene, and for this particular layer, the density will be for the silicon.
Yes.
Okay, so so here the density for this particular regime is stratified, means it is not changing, it is same. Or sometimes it's stratification people explain in different terms, like for example, these walls are there and these walls are at different temperatures, suppose T hot and T cold, okay, and one single fluid is flowing through it, suppose water is flowing through it. So the layer of the water which will be in the contact with the TH will
Yes.
be having lower density, and this part will be having the density of the water, normal density. So there will be different density for the different layer.
For the same component.
Anyway, there will be convection after some time, as the density of the upper half will
Mm.
be lower, or no, if TH is at the top, TC is at the bottom, so there will be density stratification, because but there will be different case if TC is at the top and TH is at the bottom. What will happen? What how these two cases are different? Can you explain? You see this one here, water is flowing.
Mm.
So the top layer or top molecule of the water will be losing its density.
Yes.
So lighter water molecules will be at the top of the heavier water molecule. So this is
Yet,
the
but still in this case, mixing won't be there. Like,
huh,
but in the second case, the as the lighter, I mean, water particles becomes heated because of the TH,
yeah.
it will start rising up. So
So
there will be mixing will be there.
there will be convection, natural convection coming up.
Yeah.
So natural convection coming up in the second case.
Yes.
So here this stratification will be disturbed. But in this case, the stratification will be retained. Stratification will be retained means this particular layer will be having same density. This
Mm.
particular layer will be having same density, and this particular layer having same density. So there could be a graph for the density, like if you draw, suppose this density versus this lateral dimension. So it will be like at the top there will be less density, and at the bottom there will be more density.
Mm.
So there will be a density this is also a density stratification kind of thing, means different layer is having different density. Sometimes that layer is very at the scale of molecular scale, and but in this case it is like complete the complete cell benzene and complete silicon atom. So that's it. And like in this case, you see this vertical co-current upward flow that was there.
Yes, sir.
uh, in this context, sir told that in this vertical co-current upward flow, there will be no stratified flow. Why so? Like
Sir, can you repeat the question?
in the horizontal, there will
Huh.
be stratified flow, but in the vertical, there will be no stratified flow.
Because of the gravity force,
So
the mixing was
if we want to create stratified flow in the vertical channel, how we can go for that?
electric field. Maybe we are going to
Some
apply.
field you have to apply in this particular. We suppose the channel is like this, and suppose your channel is like this vertical. Then
Yeah.
in this direction you have to apply some field, electric field or magnetic field or gravity field. If gravity field could be applied from
Mm.
externally, that could be one way to get that.
Okay.
Okay, so this question cleared up something, like you gained something out of this.
Yes, sir.
And also the video I was showing in this one, you see, uh, this is more interesting. Like this is two multi-phase microfluidics. So these are the experiments that are being performed. So you see this one, if you see, there is some condition. So what are the forces that you can think of in this phenomena that is happening? What are the forces that are at play? Anyway, this video is very fast, but it is taken in the high speed. That's why it seems like it is very slow.
Mm.
Like within microsecond, lots of bubbles are being generated. But this video has been taken in a high speed camera, so it seems small, like slow. So you see this. What are the things will be which will be at play? First is the fluid is coming in.
Mm.
So there will be inertia associated with each fluid.
Yes, sir.
Suppose water is coming from the top and the bottom, and in between oil is going. Or inverse situation can be there. Oil will be coming from top and bottom, and water will be going up. So, 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 can you think of this scenario and this scenario? Okay, first video and the third
Mm.
video. You see here we see the interface is very sharp.
Yes, sir.
The distinct boundary is there between the water and the
Mm-hmm.
oil. But in this case, the black shade is coming. There is not a very sharp boundary between the benzene and the silicon oil. So
It,
can you think of why this particular situation is there? First is the inertial, because of the flow, whatever forces will be coming up. It is powered from outside using microfluidic pump. So
yes.
microfluidic pump is like a device through which you will be pushing the fluid through the syringe into the microfluidic channel. And
So
so
one will be the pressure force. है ना?
so pressure force will be there. So that is
Yeah,
nothing but provided by the
external.
external microfluidic pump, and
Mm.
that is depicted in term of inertia. Like
Yes.
this fluid is flowing with some velocity or with some volumetric flow rate. It
Mm.
means that some head is given from the outside, and that head can be converted to the pressure head.
Yes, sir.
And another thing is like
Viscous forces.
the interfacial tension. Yes, viscous forces, correct, of the water and the of the oil,
हाँ.
and the interfacial tension between the water and the oil, gamma 1 2.
हाँ. Yes, yes, sir.
So gamma 1 2, this is the very important factor. Like in the macroscopic domain, this surface effects doesn't play much role, but in the microscopic domain, this surface forces comes into the picture broadly, and they affect the flow morphologies. Like you see, there will be different forces. For example, the viscosity, through the viscosity you told, there will be inertial influence, there will be surface influence in terms of the surface tension, and there will be contrast in density also. So density will be different for different layer. And again, the wall is up, this wall could be of different material. You see,
Yes, sir. That is also an important
that is
element.
also important factor, because through the friction of that wall, your bubble has to go. So these are the different factors that will be dictating the flow structure and the morphology of the shape that you are getting.
Yes,
So
sir.
so can you see this is not completely circular.
Hmm.
this is
Oval.
this is kind of having more lateral dimension than the transfer dimension. So this is called sludge.
Okay.
Okay, if this is much bigger than this, like capsule, then that will be plug.
Please repeat, sir.
So like there will be three cases. As a I will be writing that into the this one. See, there will be like there will be something called droplet. Okay, droplet production. Okay, so the droplet will be spherical. Okay,
Hmm.
and there will be this plug. Plug or slug. So plug or slug is having just a difference among like a plug is of this dimension, suppose. Okay,
Hmm.
and the slug, if slug will be there, this is plug, and if slug will be there, the dimension will be more. Like
Lateral dimension will be more.
lateral dimension will be more.
Okay.
This is slug. Big capsules will be there, and if this I am talking about if oil is from this direction and water is from here. Okay, in this case, oil water is thing, and if this increases a bit more, then if flow rate and everything is controlled in such a way, then there is chance that we will get this kind of regime that sir has told that is stratified thing. It is like your water is going like this and oil is coming like this.
Hmm.
So you say that this is stratified condition. Yeah,
Yeah.
but when you do the experiments, na, you will not be able to maintain that stratified condition uh, continuously like in the case of silicon oil and benzene. In the case of water and oil, there is a particular flow rate. If you do the experiment, you will come to know. You can create the stratified condition, but 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 that will not remain for the longer duration. After some time, you will see there will be sludge formation, plug formation, and the droplet formation
So
coming.
these structures like slug, plug, or droplet all depends on the I mean the
Uh, uh,
pressure force that we are applying or the flow rate that we are passing the fluid through.
and again, the property of the fluid,
Viscosity.
and in some cases people use field from the outside in order to create the droplets, on demand droplets. So field induced droplets can be created. So there is one video I haven't shown. This droplet you see, this is going straight. Okay, so it is
Yes.
undisturbed, but the wall that is at the top and the bottom, it is having electric field employed. So under that electric field, it may split like this.
Okay.
So this can happen. So this is field induced splitting.
So these are all polar fluids only, no?
Yes, that's why they got polarized. So these fluids are having some dielectric. So dielectric property is like storing charge storing capacity of the fluid. So it is having somewhat charge storing capacity. That's why this fluid got disturbed under the action
Electric
of
field.
the external electric field. So this is the I have to see like this is the microfluidic channel which is covered here. So these microfluidic channels are made in this way. You see, finally you these are the steps through which fabricating the microfluidic channel people make. So you may go through that like using these are very straightforward, easy step of fabrication of the microfluidic channel. First, you make the pattern, and then that pattern will be pushed. There is something mixture called PDMS plus crosslinker. This will be fluid like mixture. So once you make the pattern will be fixed using the double sided tape, and this uh, when you pour your 20:1 mixture of the PDMS and the cross linker, and you keep it at the 80 degrees Celsius in the hot air oven, finally it will be solidified, and you remove the wire that you pushed here using the Fevikwik. So finally you will be getting channels in which you can perform these kind of experiments.
The pattern that you used was made of wire.
So this can be made up from wire. So this is like 500 micron, na? So
Huh.
this will be like this can be you made by wire. But if it is like 10 micron, our hair is having what thickness, you know?
I think around 1 mm
No,
or
no,
1
no.
2 mm.
Our hair is like 100 to 200 micrometer.
That 1 mm only, no? 100 micrometer.
No, 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 no. 1000 micrometer equals to 1.
Okay, okay, sorry.
Mhm. So 100 micro or 200 micrometer is the hair. So this is 500 micron. So this could be made using wire. But if you are going for very thin, very small diameter channels, like
Hmm.
there's this 20 micrometer, 10 micrometer, 5 micrometer, then for that you need to have some other lithographic technique. Lithographic means make writing on the on different materials. So there is soft lithographic methods, photolithography methods through which people make different miniaturized channels, and this same experiments could be performed in those channels also.
Okay.
So that this is not, I have just discussed in general. So this question made some feel about the
Yes, yeah.
about what is happening in the
Specification.
experimental and the realistic situation. So
Yes, sir, it was helpful. I mean, it was able to, I mean, I was able to visualize things.
okay, so like the another question is which effect becomes dominant in the microfluidic flow?
Effect.
Which effect becomes dominant in the microfluidic flow?
Low Reynolds number effect, surface tension, and large surface.
So in the lectures
A, will-
also
A
said.
will also be there, I think.
So, what is non-continuum effect?
Like particles are so far away from each other that we cannot consider them to be continuous.
Okay, and like continuum hypothesis is like you are actually getting the
Yes,
average
average of.
value of the properties. For example, density, temperature, pressure. No, temperature,
But I think
viscosity.
for non-continuous are mentioned, it we can consider them to be continuous still in
Yes.
microfluidic channels. So it will also, A will not be there, B, C, D will be the option.
So, like non-continuum effect, you are saying that which effect becomes dominant in the microfluidic channel. So, answer is what? Low Reynolds
Low,
number.
low Reynolds number effect, surface
Yes.
tension will be there, and large surface to volume ratio will be there.
Large
Surface
surface to
area.
volume ratio will be there. So,
Hmm.
but in the lecture, you see, sir has also wrote non-continuum effect. So non-continuum effect we are considering, or actually in the microfluidic also it is mentioned somewhere that this continuum hypothesis is
Hypothesis.
valid.
Yes,
But
that's why.
the you see the effect size effects are what? So size effects is involving surface dominated. So if in the microfluidic you see, in the microfluidic there will be there will be size dominated effect. So surface
Hmm.
tension and those things will be coming into the picture, and Reynolds number will be very less,
Yes, I agree.
and there will be small diffusion also. In terms of diffusion will be small. That is the reason why those fluids were not mixing. You see here, these two fluids were not mixing. Okay,
Hmm.
and when in the macro scale, if we mix them in the beaker, they will be miscible. They will
Yes, sir.
miscible in the beaker, but they are not miscible in the microfluidic channel, because in the microfluidic channel the diffusion length is small, because for very small, very little thickness, very little interface thickness, there will be diffusion here only. So there they will be miscible, but entire structure will not get mixed as if it is mixing in the beaker. Okay, and that is the reason why it it seems like black. You see here in the this na, here some black region is there na.
Yes, sir.
So this is very thin diffusion. dominated region which is there. And this is not present in the case of oil and the water, because oil and water is not miscible, but benzene and silicon oil is miscible. So this will be more clear if you actually get opportunity to perform these experiments and see what is happening from your naked eyes.
Yes, sir.
Okay, and this here sir told that this non-continuum effects will be coming up in the sense like, you see, if two molecules will be there, or see any fluid which is flowing, they are consist of some molecule that
Hmm.
is specifying and fixing their identity. And for example, one of the component of the fluid will be very polar in nature, and another will be also polar, but these two polar components will be having somewhat some intramolecular interaction among them.
Hmm.
So this intramolecular interaction, which is explained in terms of dipole interaction,
Interaction. Hmm.
dipole induced dipole interaction, dipole permanent dipole interaction. So those interaction which is actually happening because of the molecular uh, electron cloud. Actually, what is happening, if any fluid is there and inside the molecule of the fluid is getting polarized because of any reason, and that polarization will be depicted in terms of uh, so anyway, whatever polarization is happening, whatever this molecular thing we are considering up, that is not the continuum, that is the effect that is arising from the molecule. So
Yes, sir.
those are non-continuum effect, and these non-continuum effects are also uh, controlled by the size. Why? Because in this particular length scale channel, this diffusion, if length scale is small, and this thing is happening, it is not coming into the picture in this case.
Yes, sir.
So in
Okay.
that terms, if you see the question that we were solving, the effect becomes dominant in microflows. These all four effects become dominant in microfluidic thing. So in the first one, as you said, the answer will be, let me take the, so answer will be A, C, and D. Okay,
Yes, sir.
A, C, and D. And in the second one, we
All
see
four.
all the four will be correct answer. So, so the lectures that sir that is there on the Swayam portal, it's like one way. You are directly not getting opportunity to communicate with the sir, teacher, instructor. It is not live one, but there is a community kind of thing there where you can post your questions, and sometimes this thing that we are doing here,
Hmm.
here you can directly ask the question. Sometimes I will be able to tell, or if not, these questions we can discuss with the sir, and that can be incorporated somewhere
Yes, sir.
at the community, or say like you may get na random mails about this week assignment has been uploaded, solution has been uploaded, those things.
Yes,
In
sir.
that particular framework only, sometimes the questions and the corrections can be made.
Okay.
Okay,
Yeah, I was able to find the discussion forum also, but only three mail messages were there in that. I think I didn't. I mean, I haven't shared any doubt in that.
you can say
Every.
there will be some it will take some time, because from the end of teacher or whomsoever will be the responsible person, so it's like a team is there to control whatever
Hmm.
happening. Okay, so the normal stress is the same in all direction at a point in a fluid when the fluid is, options are non-viscous, incompressible, both non-viscous and incompressible, And the last is having no motion of one fluid layer related to the other fluid layer.
Stress is same in all directions.
So the normal stress is the same in all direction at a point in a fluid when the fluid is non-viscous, incompressible, both A and B having no motion of one fluid layer related to the other fluid layer. You can try, you can think of whatever whatever uh, concepts is getting up into the mind. This is why these sessions they have arranged.
Stress in all directions at all.
So
I think A B is the, I mean, having no motion of fluid layer.
so sometimes there will be like multiple choice one, or sometimes there will be it is not written anywhere, but all the option can be correct or only one option can be correct. But in the quizzes, I think only one option is correct. Na? Assignments.
In the assignment, yeah, only
Uh,
one is correct.
we are told to keep questions somewhat more involved.
So I think in this, incompressible will be the option. Normal stress and non-viscous. Even if the fluid is non-viscous, we have normal stress. And even if the fluid viscous, then also we have normal stress. So I think
And this
A, B,
incompressible compressibility, does it play a role in the normal stress?
uh,
So what is actually happening? See, the fluid. Suppose this fluid is there in the container, okay,
hmm,
and this container here you are having this particular point, and from all the direction there is force
hmm,
coming up. These are nothing but the normal stresses which are being
yes,
generated at a particular location in the fluid. So even it is viscous, it is non-viscous, or it is having some density change or not change in the density also. So this will not play any there will be no problem at the level of normal stress. So having no motion of one fluid layer related to the other fluid layer. So you see this normal stress is the same in all the direction at a point in a fluid
hmm,
when the fluid is having no motion. So if, for example, this fluid is there and this interface is there between them and this motion is there.
hmm.
So if relative motion comes up into the picture, then
Shear stress will come.
then the normal stress, the force balance which is there, that will be
Hmm,
disturbed. And at the interface of the two fluid, there will be balance of the forces. So can you tell what are the forces? Force balances will be there. For example, I will be doing that here, right? Uh, in this one. Okay, for example, this is the situation. This is the third question. So in this one, if this channel is there, okay, two fluids are coming up and one fluid is coming from the front, and this fluid is coming from here and here, and this interface is created. Okay,
yes, sir.
So so at this wall is fixed, so there will be u equals to 0 kind of condition here. U equals to 0, or say v is the velocity in the vertical direction. V equals to 0, v equals to 0. So suppose a datum you have considered here z, and this is x. So here at z equals to 0, v equals to 0, at z equals to suppose diameter, v equals to 0 also. Okay,
Hmm.
and this is the interface. So here suppose you in the normal pipe flow there will be this kind of velocity profile,
Yes, sir.
but here as two fluid is there, there will be velocity, there can be different velocity profiles. For example, like this there will be maximization, then
Hmm.
there will be more velocity. If this particular flow which is coming up, it is having more velocity than this, then maxima will lie in this particular layer. Okay,
Hmm.
and then if different is the case, then maxima may lie here, or maxima can lie at the interface itself. So this particular interface which is there, this particular interface whenever you see in any experimental setup, this will not be fixed. There will be somewhat undulation there. This will be having somewhat motion in terms of that's why in the experimental setups or in the research papers you see this is shown to be somewhat fluctuating, somewhat like this. Okay, I am not able to draw it. I don't know why. Okay, huh. So there are four balances that is here at the interface. First balance is the tangential balance in this direction. Second is the normal balance in this direction. Then continuity of velocity will be there. So what will be there? For example, this is the interface here. There will be normal balance. If a molecule is here and if this molecule has to be here only, then whatever force will be there at on this molecule from the top and from the bottom is to be that has to be equal. So that is nothing but the normal balance.
Normal. Hmm.
And another one is the tangential balance. This is because of the shear.
Hmm.
So if this molecule has to be here only, then whatever force it is feeling in this direction and whatever force it is feeling in direction, that has to be equal.
Yes, sir.
So that is tangential. And also u1 equals to, if this fluid one was the top one, then whatever u1 is there here and here u2 is there, then u1 equals to u2. This is called continuity of the x direction velocity. And another one is v1 equals to v2, continuity of y direction velocity. These four boundary conditions will be there at the interface between the two fluids, and this is the this is the point where there is a chance of disbalance in the normal balance. So in this question, it is like the normal stress is same in all the direction at a point in a fluid when the fluid is having no motion. If there will be motion, there will be these forces, these balances coming up at the interface. So at the interface, there is chance that this normal balance will get imbalanced.
Yes, sir.
So in this one, what is the answer? Having no motion of one fluid layer related to the other layer. So option
D.
D is the correct answer. Okay. So this one is basic fluid mechanics. You see,
Dimensional electricity.
flow of Newtonian fluid ceases to exist when the Reynolds number exceeds 4,000, 2,100, 1,500, 3,000.
2100. Pipe flow के लिए ना. This is for pipe or
Yes,
channel flow.
yes, channel flow.
21.
So
2100.
Below 2100 is the,
laminar,
so less than 2100 is laminar, laminar flow, and greater than 4000 is
turbulent,
turbulent, turbulent, and between
transition.
is the transition, transition flow result. So this is for what? Pipe flow,
Pipe flow, internal flow.
internal flow, and this will be different for open channel flow.
Yes, sir.
So can you do you know the rough figure about that? What is the value of Reynolds number in that case?
External flow, for external flow, it is approximately 10 is to power 5. Less than 10 is to power 5, it is 2 into 10 is to power 5, it is. Then it will be within laminar flow regime.
And also one question that I always ask is like, in this pipe case, you define your Reynolds number as rho v L by mu. Okay,
Yes, sir.
and in this case, this L is a characteristic length, and which is the diameter of the pipe itself.
Yes, sir.
Am I right?
Yes, sir.
Okay. And if in some cases you see uh, flow past some submerged sphere kind of thing, if that will be there.
Hmm.
So if a sphere is there and around that flow is happening, so in this case, if analysis of drag on the sphere is happening, then at that in that case you define Reynolds number using the diameter of the sphere.
Hmm. Yes, sir.
Okay, so how you define Reynolds number in open channel? Have you ever thought,
Uh,
or
like if the cross section, I mean, let's say if the plate is there,
yes?
of cross section L, H, length, as well as the length along the length which along the length
Okay,
flow is
so
happening, and
let
H,
me draw that. Whatever you are
yeah,
saying, a plate is there. Suppose.
let the length be L and the width be H or
Okay,
W.
this is H. Okay,
Uh,
W. Say
so
W. Width.
uh,
So and flow is
so
happening here. Flow is happening here. Ah,
yes,
this is open channel
so
flow. And in this case, you say this is the boundary layer forming.
yes,
And so in this case, how this Reynolds number is defined. So you think about this. If you exactly know now, only you can tell.
so L is the length we take as the characteristic length
So
because the flow is happening along the length.
so how this characteristic length for defining Reynolds number is taken, that you think about. This is a good question that may be thought of, and similar kind of troublesome students feel when they are actually dealing with this Biot number and the Nusselt number. So in the Nusselt
Yes,
number, there will be a diameter coming up, and in
yeah,
the Biot.
4A, there's some 4A by P formula that is the hydraulic
Yes,
diameter.
yes. In that, there also there is confusing. So you clear these characteristic dimensions that need to be taken in different kind of flow situations and the geometry. So based on that also. So if you just think of, you just have to see in some standard book or the lecture that what they are
Hmm.
taking and why. Just when we read those things first time, we don't think of that, but at the end we come to know
In
that there is
in
something.
case of Biot number, generally what they take is the volume by surface area they take.
Yes.
So whatever is the volume of the substance or the body and divide by the surface area through which the flow is happening.
So what is
And
biot number?
it is the ratio of the
So let's
heat
talk about
conduction,
that only. So biot number is
the ratio of heat conduction resistance divided by the conduction resistance.
so conduction resistance, resistance. Okay, divided by
Convectional resistance.
in what?
Let's suppose if a body is cement, the conduction resistance of the body is, for example, there's a ball, oh,
Hmm.
let's say that. So the conduction resistance for that, uh, we have to
Okay, okay.
mention
See, conduction resistance of body you said means
the body
of some
of the
solid,
solid,
of some solid,
of solid.
of
Yeah,
solid,
solid.
because there will be conduction. And the
Mm.
convection resistance of what? Fluid surrounding the,
Fluid. Yeah.
no, convection resistance of what? Solid only. This is the grid. This is the very important point that
Yes,
if,
in Nusselt number, there's fluid comes in, and in Biot number, solid comes in.
so here if you write it, the conduction resistance in the solid will be somewhat L by Ka, if the L is the characteristic length of that particular solid, if,
Is
and divided by
1
what?
by
1
HA.
by Ha.
Yeah.
Ha is the
Yes, sir.
resistance,
HA
convective resistance, that is because that is there, and this will come out to be HL divided by
by K.
K, what? K what? K
K
what?
of solid.
Solid. Thermal conductivity of solid.
Solid.
And they, in the Nusselt number, this K is also coming up.
Yeah, that is for fluid.
So conductivity of fluid.
Because conductivity do comes in over there because when we are analyzing that, we consider the uh, no slip condition, and that no slip condition that uh, the liquid, the fluid behaves as uh, behaves as a conducting body. That's why we
Yes,
consider K of fluid.
for that thin
Then for
particular
thin
layer of the
section,
fluid.
mm,
Okay, and now in this, I was talking about this L. The choice of this L is also very crucial. Like very standard body, we easily get that. But if for example cube is there, then there is no problem. But if cuboid is there, which one is facing in what way to the convective cross sectional area, that has to be accordingly, we have to choose. And what is Nusselt number?
that is also conduction resistance by conduction resistance only.
Resistance due to conduction in the fluid. Okay, so conduction in the fluid, resistance of fluid divided by what? Resistance due to convection in the fluid. So
Convection.
both
Yes,
is
sir.
for the resistance of fluid. So yeah, again, if you derive that, exact same formulas will be coming. Just the K will be for the fluid
Fluid.
here. So when you solve it, you get HL by K fluid. Actually, at the time of somewhere I did this mistake, and then I
Yeah,
came to
this
know.
this sometimes comes in again and again, and I'm also falter in this.
Hmm.
I don't know.
So, what do you feel like if Nusselt number is greater than one? For many, in general, for many fluids, Nusselt number is more than one. Okay, so this Nusselt number is more than one means what? This conduction resistance of the fluid will be more than convection resistance of the fluid.
Yes, sir.
Conduction resistance will be more than convection resistance. Okay, means Q conduction will be less than Q convection. Means heat transfer through the conduction will be less.
Less than the
So
convection.
Q conduction will be less than Q convection. Okay, means convection will be more in that case. So if Nusselt number will be more in some situation, there will be moving fluid result in the more heat transfer. Okay,
Yes, sir.
if the Nusselt number is greater than one, in that case, the heat transfer will be more if the fluid is moving. So that is it. So let's come to the question, because lots of question we have to do. Still we are having 1 hour, so now we will be rapid fire. So 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 now fifth question is the fluid property due to which mercury does not wet the glass is the surface tension context that
Addition.
sir told. The concept of surface tensions are told now.
Yes, sir.
The
Contact angle.
contact angle, mercury does not wet the glass is the surface tension actually. And if
Cohesion.
cohesion can
You
be there, adhesion can be there, you think surface tension arises because of what, cohesion or adhesion? So which option do you think is the correct? A only, or AD, or AC? A will be the correct one.
AD addition. I mean, addition is because of the particles interacting with other particles. So more is the addition, more is they are interacting. But mercury doesn't.
Means there
Uh,
is no adhesion.
no,
Means
negligible addition.
A and C.
A and C.
A
A
and
and
C
C.
is the
Yes.
correct answer. A and C is the correct answer. Okay. And then this one, what do you think about this? Shear stress in the fluid flowing in a round pipe.
I- for-
Shear stress in a fluid flowing in a round pipe. My
Is
both the
zero at the
screen is
center
both
and
the screen is
yes,
visible,
sir,
na?
it's visible.
Okay.
Visible. Yes, sir. Is zero at the center and varies linearly with the radius.
Zero at the center and varies linearly with the radius. Okay. So how you are thinking about that? Like in the class also maybe sir told it. I think this is the pipe. Okay. And here you know that if fluid is flowing, there will be parabolic velocity profile. Okay.
Yes, at the center velocity is maximum and at the top the
This is radius r.
walls
So you are saying that u equals to u max
at
1 minus,
center R by capital R oh, square.
this is the parabolic thing. And if you are talking about shear stress, then it will be tau is equal to mu del u by del z. Or if it is y
Yes.
direction and it is x direction, then del u by del y. So derivative of this when you will take,
Hmm.
so this is r direction, I think. So this should be r. Okay. So del u by del r when you will take, then you will be getting 2r minus 2r will be coming up. 2r, if you differentiate it, this u max part will be 0,
Yes,
and
sir.
this will be like 2r 2 minus 1. So from here we see that del u by del r is directly proportional to the r. Means this tau will be directly proportional to the r.
Hmm.
Means this the shear stress profile will be linear.
Yes, sir.
Linear. So linear is given in the C and D. But accordingly, now you understand, if there will be no sleep and near the wall there will be more of the wall effect, there will be more gradient in the viscosity velocity because of the wall, and there will be more shear stress. So accordingly you think of that, there will be velocity profile for shear stress like this:
Yes, sir.
zero at the center and
Linearly with the
linearly
radius of all.
symmetrically increasing, different in different. If both the center is not at the this center line is somewhat in between, then there will be some different situation. Okay. So this is it. And the seventh question, you see, the dynamic viscosity is the mu. There is two viscosities. One is the dynamic viscosity and another one is the kinematic. So this is the dimension of the dynamic viscosity, and here the dimension of the kinematic viscosity here. This one. So kinematic viscosity is nu equals to mu divided by density, and dynamic viscosity is the mu. Yeah. It says like you may start with the tau equals to mu del u by del r. So from there you can.
Dynamic viscosity. T minus 2.
During bachelor's time, these are like on tongue. We can directly say. Now, gradually we are heading in higher classes. These basic questions are like, pen, we have to calculate it.
Yes, sir.
Yeah.
That immediately by delivery. It's like
So I will be doing it. So this mu, you see this tau is there, na? So this mu, if you see, this mu equals to this tau is what? Force per unit area.
force penetrate, yes, sir.
Force per unit area equals to mu.
Uh,
And this is what? U by R means meter per second divided by
yes.
meter.
Hmm.
And this F is what?
MLT minus
MA.
1.
MA.
MLT minus 2.
Okay, I understand. But this is mass into acceleration.
Yes, sir.
Mass means kg. Kg means m into acceleration means L
LT minus
by t2
huh.
divided by
L square.
L square divided by this L square. And this
Hmm.
one we know that this is what? This is m, this is t, this is again m. This is L, this is
Yes,
t, this is L. L cancels. So only
yes,
1 by
sir.
t this direction. This side we are having
Hmm.
1 by t.
Hmm.
So you just rearrange them. So this t will be going that side and t will be getting cancelled.
MLT minus 1.
So m l minus 1 na, because L will
ML.
be cancelled.
L minus 1. Yes, sir.
T minus 1.
This one.
This is the dimension for this. Okay. And similarly, if you
For kinematic,
kinematic
we
one is
divide we divide by density.
so ml minus 1 t minus 1, you know, this is
Yes.
ml minus 1 t minus 1, and this density is what? Density is kg per
Kg
meter
per
cube,
meter cube.
means
That is
m
M
l
by
minus
L
3,
cube. Hmm.
ml minus 3. So then what you are going to get?
L2T minus 1.
M
B.
L 2, m will be cancelled,
Only M will be cancelled. L2T minus 1. That is the B option.
L 2 t minus 1, and this will be cancelled now.
M will not be there.
So what is correct one? L 2 t minus 1 is the B option. And in this one, what is this? This is ML minus 1 t minus 1. A option. Okay, A is the correct one. And the another one, this is like somewhat informative. I just kept it. Maybe you know it. Brownian movement is predominant in the particle size range of you have to choose the options micron in case of settling of the particle in a fluid. So suppose a fluid is there, okay?
Hmm.
A fluid is there, and suppose water is there, and in this lots of gold particles are there. Gold nanoparticles are there. Okay, gold
Water.
particles are there in water. So,
Okay.
do you know that gold is of what color?
Golden.
Golden means yellow, yellowish kind of thing.
Yes, sir.
But what will happen if this uh, gold is the whatever gold you are having now,
Yes,
you
sir.
crush
Hmm.
that, reduce that size, and all the particles that you are having, they are either in the micron or in the nano size, like 10 nanometer particles you made from the gold that you are having, that is golden in color. Then what will be the color of that solution, that if you disperse them in the water?
The water will also have similar color.
Golden color na.
Hmm.
But that situation is different. Do you know why? So if I can use the internet, if internet is there, so I can tell you. Wait, let me see. So yes. So what is the situation like? This gold nanoparticles now, it will be
Yes,
red
sir.
in color, dark red, from golden color to the dark red.
But how?
But how? That is the thing. But this PC slows down. So let it get comfortable, then I will tell. So there is something called surface plasmon resonance that happens at the surface of the gold, platinum, and silver. These are three materials. If these three materials are reduced to the size which is nanometer, like nanoparticle you are making of them, then they will give a specific color for the specific colloidal solution of size of that particle. And I will show once this glitch will be not there. So I will show that the particular thing. Na? So
Okay, sir.
this Brownian motion is predominant in the particle size range of 2 to 3 micron in the size settling particle. So Brownian motion is like, Brownian motion means what?
The zigzag motion, like in the morning, if wake up and then we turn, I mean, if we allow the sunlight to pass through in our
A
room,
small hole
there will
from
be
the
a
small
small part.
tidal effect you are talking about.
Ye- That is not the Brownian motion.
No, that is volume motion. Tidal effect, which is coming up in
Yeah,
that particular light path, you see small molecules are moving. That is the Brownian
particular.
motion. Na? So it means
Uh,
that in our air, lots of small molecules are roaming around,
yes, sir.
and lots of these small molecules are somewhat, when we breathe, they are going into our through our this
In our lungs.
respiration path, and that's why
Mm,
in Delhi lots of problem is there where you are.
yes,
Okay,
sir.
so pollution problem is there, na? So there you will be able to see better tidal this Brownian motion.
Mm. That's why I gave that example.
Okay, so like this, this is the somewhat informative, like 2 to 3 micrometer size particles. If they will be there, there will be predominant Brownian motion. If Delhi atmosphere is having this particular range of the size, then there will be
Mm,
predominant Brownian motion happening. Okay,
mm.
so A will be the correct option for this one. Okay,
Okay,
and
sir.
then this one you say, tell which of
Uh,
the following is not concerned with the fluid particle interaction.
I may not be able to answer this.
So what are the numbers that sir taught in the class?
I have watched till third video. I mean, third
Ah,
video I watched partly.
okay, third video was partially, but in the class, I think sir told about the Weber number, and this Weber numbers are told, and this a Fraudy number. What is that?
Inertia force to gravity force.
Is the Fraudy number?
Huh.
Fraude number is the inertia force to the gravity force, and Galileo number.
Galileo, I don't know, sir.
Galileo number you
Galileo.
don't know. Okay, so this particular, there is a slide sir told. I wanted to show exactly. In that, there is a question that he posed, and that is of our interest. This okay. So what is this drag coefficient? CD is the drag
CD.
coefficient.
Yes, sir. CD.
So
Centimeter.
what is that? Mhm. Yes. So sir told about these numbers. Weber number is like inertia force to the surface tension force. Okay. So
Weber, yes, sir.
this is inertia force to surface tension force. Okay, surface tension force. From here it is clear that this will be rho v
Yes,
square
sir.
divided by sigma upon d. So it will be rho v square divided by sigma is the surface tension. Sometime we write it gamma by d. Okay, so
Hmm.
this anywhere this is involving fluid particle interaction means the behavior of the fluid at the wall. So
Yes, sir.
this drag coefficient, we actually see this fd equals to cd rho v square divided by what 2. So
Yes, sir.
this is there when drag is happening on the particle, and particle is in essentially the solid one. So this will not be the answer because this involve the fluid particle interaction thing. And the Froude number and the Galileo number, these both the numbers you see, this Froude number involves the gravity acting at the particular particle.
CD is specific to the solid.
Yes, CD is not specific to the solid, rather experimentally calculated, and this CD is like a shape dependent property. And again it depends on shape of that particular particle which is being forced and which is under drag, and also the orientation of it.
Okay.
Okay, and this Froude number is the ratio of the inertia and the gravitational force. Okay, inertia divided by gravitational force. Okay, and this
Hmm.
gravitational force of what on the particle. So this Froude number is again depends on the particle. And this Galileo number, you say you can also look at like any notes or something you are having Galileo number. Okay.
Galileo I have not noted. I mean, I cannot find in my notes. I or I missed something.
No. In that Galileo number is also like it's proportional to the gravitational force. So like this is proportional to gravitational force divided by this gravitational force divided by viscous force
Okay.
divided by viscous force. Okay, so this is again involving the gravity, so the particle and the mass. So only the clear winner here is the Weber number. And also in the sir's lecture also, sir has taught this Weber number context in terms of surface tension, which is at the interface of.
RE into CA,
Hmm.
capillary
Hmm.
number and RE number.
So here the answer is which of the following is not concerned with the fluid particle. That is the D option, which is Weber number. The dimension of the surface tension. This is straightforward. You can say surface tension is
Force per unit length.
force per unit length. So A option is the correct one. Okay.
Yes, sir.
And the 10th one is which of the following is
Okay.
not dimensionless parameter. So Nusselt number is a dimensionless parameter.
Yes, sir.
Fanning factor, fanning factor comes up in the Moody's chart.
Yes, sir.
This is there in the Darcy number. HF equals to
Uh, FLV
4FL
square by 2
V
GD.
square by 2GD.
Yes, sir.
So this F is the factor. It is not having any unit,
Hmm.
but the
And the
specific
specific
gravity.
gravity,
Specific gravity is the. So
sir.
what is its specific gravity?
Weight per unit mass.
Weight per unit mass. Uh,
I think, yes, sir.
hmm,
Rho G.
hmm, correct. So B option will be correct answer. And then 11th one, you see this one, for a given, for a particle settling in water at its terminal settling velocity, which one of the following is true? So maybe this image will clear it up a bit. This one, I will copy this here for your reference. Now it will clear. A particle is there, and this
Hmm.
particle is trying to settle down.
So the gravity force is being balanced by the drag and the buoyancy force.
So drag will be there. So drag, what is the formula for drag of a particle moving under the Stokes limit again? So Stokes limit, that because of this question, I have kept a question on the Stokes limit also. So first you come to here. What is the Stokes law? Stokes law is valid when the particle Reynolds number is less than, like, very less Reynolds number. If very less Reynolds number is there, then there will be
Less than one.
there will be this there will be this coming up, uh, Stokes law correlation coming up. So actually 0.01 or less than 1 means it will be less than 1. So if the re,
Very low velocity, no?
very low velocity,
Terminal velocity.
uh, then in that case there will be this Stokes law will be valid, and in that case this FD equals to 6 pi eta RV, which is there, this will be valid in the Stokes law limit, Stokes regime. And the answer will be like buoyancy force plus the drag force, it will balance the weight. And what is this 4 FL v square v, 4 by 3 pi r cube into rho? This is mass
Mass.
density multiplied by the volume
Volume.
of the particle. So in that sense, you see this B, no, C, B is the correct answer. B is the correct answer for this, and this one is B here also. Okay, and this, the velocity profile for the turbulent flow through a closed conduit is
Logarithmic.
logarithmic. How you know that? This, like, you read or you derived it somewhere?
I didn't derive, but I have read it.
You read it. So what is the expression for that conduit one?
Expression. I cannot recall exactly.
I kept it here to tell somewhere. Yes. So this particular thing, you see this, for this is if you take r common na,
Huh.
then you will be getting this particular expression, u max 1 minus r square by r square only
That's for laminar
for the
flow.
laminar flow
Hmm.
velocity distribution. And for the velocity distribution, if you consider for the turbulent flow in a smooth pipe, then it comes up to be u infinite divided by k ln y plus c. And this k is again roughness, and this ln y, from here we see that the velocity profile is logarithmic.
Logarithm.
And maybe in the upcoming lectures or in the basic fluid mechanics it is there. So this,
Hmm.
so we were told to incorporate some of the basic fluid mechanics question, and again the questions relevant to the week that is going on. So what is Mac number, and which Mac number, Nusselt number, Renault number, and the Weber number?
What is the following limits? Mach number.
Okay, Mach number is correct. So Renault number, inertia force upon viscous force.
Yes,
This
sir.
is inertia divided by viscous force. And Nusselt number, we
Hmm.
just talked that this is conducts
HL. Okay.
HL by
Of fluid.
K of fluid, and Weber number we just
Inertia force by surface tension force.
inertia force by surface tensile force. So Mach number is the winner here. So what is Mach number, and what value? What is the cutoff Mach number above which, below which, or around which you will be having this compressible situation, incompressible situation, and so on.
That is the value of C. I mean, Mach number is correspond to C by A, where C is the speed of sound in that medium, and A is the
Hmm.
uh, velocity of the particle that is moving. So, if this ratio is less than zero point 0.3, then we consider the compressible effect to be negligible.
Okay, less than zero point 0.3. So this M is less than zero point 0.3. Then what will be condition?
Incompressible fluid,
Incompressible
incompressible flow.
flow. So what is this incompressible fluid and incompressible flow? Have you ever thought this?
Uh,
Fluid, you understand that whatever is not changing its density,
uh,
or there is only very less percentage of change in the density with something, some effect.
yeah, change in density upon the density. If it is very less, then we consider the the fluid to be incompressible. But this, for the flow to be incompressible, this condition has to be satisfied that the
Mach number one
is
that you
less than
told,
zero point
less
0.3.
than zero point
Yes.
0.3, and this is actually governed with the velocity of ratio of the sound velocity to
Uh,
the velocity of the,
particle.
and this one we solve like kinematic viscosity. Okay, this one you see the fluid in which the shearing stress within it is proportional to the velocity gradient across the sheared section. Okay,
Newtonian.
and this
This will be the Newtonian fluid.
okay, Newtonian is the correct one. And then what are something about the Bingham fluid?
Bing, Bingham fluids are those fluids like if we in like shit, I think
There
shear thickening. Like if we increase the shear stress, uh, s- they get thickened.
okay. So
Like two types of fluids up in this case,
for
Bingham
example,
and
this
pseudoplastic.
okay, wait, this one, if you see this curve, which is standard curve for a different type of fluid. So here you have strain rate at the x-axis position, and
Okay.
this
Shear
shear
stress.
stress at the top. So this one is the Newtonian.
Hmm.
Okay, so this is like Newtonian fluid. And what is the Bingham? Bingham will have some
Will
threshold
increase.
shear stress at zero shear rate itself. Bingham. And what are these two? Just for the sake of revision, what are these two?
dilatant and
Which one is
pseudoplastic.
dilatant and which one is pseudo?
The one which is increasing, like the below one, the lower one is the dilatant, and the other upper one is the pseudoplastic.
This is pseudoplastic. So these are the fluids. So these are anyway having non-linear,
There was one question.
non-linear with decreasing slope, non-linear with increasing slope. This one is non-linear with increasing slope. This one is non-linear with decreasing slope, and this is linear with the constant slope. And again, Bingham
Yes,
is also linear with the constant slope, but with a non-zero intercept.
there was a similar question related to this in the week zero assignment.
Hmm. So what was
But
that?
it was quite confusing. Let me just see once a minute, please.
In the week zero
Like
assignment.
non yeah, non-Newtonian fluids in which apparent viscosity decreases with increasing stress are called pseudoplastic, Bingham plastics, dilatant, and thixotropic. These are the four options.
Again, I will be writing uh, what you said.
Yes, the question was uh, non-Newtonian fluids in which
Okay.
the apparent viscosity decreases with increasing stress.
Okay. Apparent viscosity decreases. Okay, with increasing stress. So there is two fluid, na, rheopactic and thixotropic.
Yes, sir.
So in if for those fluids, you actually plot those two graphs like U apparent at to the strain rate. So I mean that particular things, if I am having that right now, this thixotropic one.
Those two graphs will come just along with the
So
Bingham
what you said,
fluid. Like
the non-Newtonian, what was the question? Let me write so that
yeah,
non
non-Newtonian fluids in which
non-Newtonian fluids,
in which the apparent
in which
viscosity
the apparent
decreases with the
viscosity decreases
dec- with increasing stress.
with increasing
Yeah,
stress.
are called
Stress. This is stress.
increasing stress. Only increasing stress is mentioned,
Are,
not shear stress.
okay. Are called
Options में है, like in options there is pseudoplastic,
pseudoplastic,
Bingham plastics,
Bingham plastic,
dilatant, and thixotropic.
dilatant, and thixotropic. No?
Yeah, yeah.
Tropic. Okay. A, B, C, D. Let me try if I can. Okay. So thixotropic. Okay. So apparent viscosity decreases with the time. So with the time, it is explained.
No, it decreases
With the time.
with increasing
But
stress.
here it is said with increasing stress, what will happen? So stress is
Uh,
actually the tau one. So with respect to
if time is there, then it will be thixotropic. But since there is no time, I marked pseudoplastic as the option
so why you mark pseudoplastic?
because if we go over the graph that you had drawn earlier, the dilatant with dilatant fluids, the stress was increasing,
Hmm.
and
So
with pseudoplastic, stress was decreasing. There was a non-linear curve, but the it was
but
decreasing.
stress was decreasing. But what
Hmm.
about apparent viscosity?
Apparent viscosity. Uh,
How
I
apparent viscosity depends on the I mean this shear stress.
tau by del u del y. I
So
considered
let
that
me explain you the that thing. For example, what is apparent viscosity? Okay, then this apparent viscosity, this apparent viscosity, this apparent viscosity. One thing you know that this is tau equals to mu du by dy. Okay,
yes, sir.
this is the standard formula for the stress, and then this mu, sometimes people write it like tau equals to This mu na, this here mu is going to change, and it's not property and called apparent viscosity. So this is in general, but for non-Newtonian fluids there will be this mu will not be the same. Mu will be changing with the strain rate also. So this mu should also have for non-Newtonian you will write Q equals to mu apparent multiplied by du by dy. Okay,
Okay.
to the power n. That means there will be this mu to the power this n, and then this du by dy to the power n minus 1. I mean, how I will say this, the formula for the mu apparent is mu du by dy to the power n minus 1. N is a constant, so the n will be having its value positive, greater than 1, less than 1 in the case of dilated and the Newtonian, this pseudoplastic, and n equals to 1 for the Newtonian.
Newtonian fluid.
Okay, so this mu apparent, so for the pseudoplastic you know that for the plastic this n is less than 1, and it is n equals to n equals to 1 for what?
Newtonian.
Okay, for Newtonian n equals to 1 Newtonian, and for dilatant this n is
N greater than 1.
greater than 1. Okay, so this if you say this in terms of, actually here time is not there, so that's why apparent viscosity decreases with the increase in shear
Stress.
shear shear rate. I mean they should have mentioned it. Is through the stress it is a bit difficult to think.
It was like
So have you may raise this question in the community, okay, then we will see actually is this
this was the question. I just wrote in the chat box this question. I mean,
you wrote it. Actually this PC is like hand up, so that's why I am not changing it, because meeting is going on anyway. Okay, so I will see it, and you may raise this in the community at the on the Swayam portal. Okay,
okay.
okay, but this should be connected with the one that we are having this mu apparent, this mu apparent. Okay, mu apparent
Hmm.
with the shear rate. If it will be there, then for the pseudoplastic and for the dilated, this is for the dilated, this is for the
Hmm.
pseudoplastic. This is the scenario that will be there, but this will be with the shear rate, and then we will be looking at, and I will be thinking of this. So if you see when for the pseudoplastic, what
Hmm.
was happening, yours
If the shear strain rate is increasing, then the stress is decreasing. So if we try to plot this way,
in
ki
these terms
on the exact,
you will be able to get something out, I think. And here mu apparent versus time, you when you plot, this is for the thixotropic, this is for the rheopectic
it increase, rheopectic
and
increase, and thixotropic decreases.
thixotropic. Okay, but from this graph I think that question can be attempted. So this pseudoplastic and dilatant, no, this was the question, pseudoplastic dilatant, this was pseudoplastic
Yes.
plastic, and this is dilatant, this is du by dy, this is mu apparent. Okay, and the one that you had, this is for pseudoplastic and this is for dilated.
Yes, sir.
tau and du by dy. From here, we have to think of mu versus tau, mu apparent versus tau, if we can claim. With the shear rate for the pseudoplastic, tau is increasing. Okay,
Hmm.
but the rate of increase in tau is getting slow. Okay, so this will be like this. How I am thinking? No, 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 no. See. This with this strain rate, tau is increasing,
Yes,
and this tau is increasing with the strain
but
rate.
mu apparent is decreasing with increasing tau, increasing rate, strain rate.
Strain rate mu apparent is decreasing with this three. Actually, this is not that straightforward, as if
Uh,
something is not given, na. Okay, so you just post it on the on that community, then I will ask the instructor to look at it. Or
okay,
actually, there is separate TA for the assignments that you are being posted at the on the portal, and separate TA for the live session. so so
okay,
so it's
okay,
like that. So we will together get it sorted, or if there's some change need to be done in the question itself.
okay, sir.
Okay, okay. Good question. You are actually digging deeper. Ah. So Stokes one is clear. Which one of the following is not dimensionless parameter? You solve it, I think.
So the following is not a
It
dimension.
is also easy one. Kinematic viscosity is having some dimension.
Yes,
It is
sir.
meter square
Kind of
per
second
second. It is mu by
row.
rho. Also, you had its dimension today. You calculated it. L2
Hmm. LT minus 2.
t minus 1 now.
L2 T minus 1.
Hmm. And next question is, which of the following is not observed in the vertical concurrent two-phase flow? Vertical one,
Vertical stratified.
stratified. This is similar to the one question we solved now.
First question we solved.
At the molecular level, separation between the two
Two
immiscible
meters.
fluid depends upon.
Level separation.
This could be single choice or the multiple choice.
Molecular level separation. Immiscible fluids are there, so how, I mean, they will be definitely be separated itself. So,
Okay, I understand that. At the molecular level, separation between the two immiscible fluid depends upon. So, two immiscible for oil and water will be separated anyway.
hmm,
But at the molecular level, at the interface, as if you are there and you are looking at the molecule of the water and the molecule of the oil.
hmm.
So, they are separated. So, what are the forces because of which they are separated? And what are the forces that is helping them to be separated? So, obviously, uh, uh,
Brownian diffusion will not be there.
Brownian diffusion, molecular interaction between them, dipole dipole interaction between them, induced dipole, permanent dipole interaction between them.
I'm not able to get this question actually.
Actually, this question says if oil is there and this water is there, they will
Hmm.
create the separate interface.
Yes,
This
sir.
interface is there. So you say that this interface will be stable and there will be no diffusion.
Hmm.
So So what is helping that to be in that particular stable situation? So
Okay.
I mean,
Molecular interaction between them.
okay, molecular interaction between them is like it is not allowing them to mix. So
Hmm.
actually, you have to go at the origin of the surface tension here. So surface tension is the one that is not allowing them to mix
Yes, sir.
somewhere. So
Uh,
so 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 what is the basic origin of that is the molecular interaction between the two molecule of the
sir, fluid.
fluids. So B is the correct one. See, this one sir has explained. It's for the revision, like continuum
In
hypothesis.
this, in the 20th
Yeah.
question, there's no you. I mean, I mean
So
involvement of this dipole
actually,
interaction or any.
yeah, if this is correct, now these two will also be correct because these are nothing but the molecular interaction. So B, C, D will be correct. You are right.
Dipole, like they only come if the fluid we're talking about is like polar.
Uh,
Oil not necessarily need to be polar. I mean, which it depends, no?
no, it depends, but it can be polar. So in general, you will like water is anyway polar.
Water is anyway polar.
Oil can also be polar. There will be hydrophobic group, but you know that there are many hydroxy based oils and this triglycerides. So these
Okay.
are having this kind of bonds between O C double bond O kind of setups. So here electronegativity gradient between these at this bond level, there will be some induction in the charge. Induced charges will be there, though they will be not exactly polar like water, but there will be some characteristic which will be having uh, polar nature.
Okay.
So this BCD will be the correct one. This
Okay. In the lecture, sir also talked about some amphiphilic substance. What is that amphiphilic?
amphiphilic.
He talked about hydrophilic, hydrophobic, and prior to that he talked something about amphiphilic. I couldn't get that, but I could get hydrophilic, hydrophobic, the word which is there.
Hydrophobic is like based on water, like water loving, water hating,
Yes, sir.
and then there is something called oleophilic, oleophobic, oil loving, and
Mhm.
oil hating. I am
Yes,
not
sir.
able to go at the.
In the topic when he talked about surfactants.
Hmm.
So in the second line he mentioned long amphiphilic molecules having hydrophilic head and hydrophobic tail.
Long
Long
amphiphilic
amphiphilic.
molecules. Oh, amphiphilic term is used if a molecule is having both the characteristic.
Okay.
Like that is having oil loving or oil hitting group also. As far as I remember, actually, I have to look at where sir told each one.
In the topic surfactants and in the lecture,
I think
lecture
second lecture.
second lecture, yes, the second lecture surfactants topic.
So yes, so amphiphilic is like na, there is like uh, 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 a cationic buffer, anionic buffer, and there is a buffer which is having both characteristic. So
This is more of chemistry.
uh,
I need to revisit.
so it's like that only. Like in this case, amphiphilic means MP. The word MP means what? Can you search it? Amphiphilic.
Let me
Actually, internet
search it.
is not there. Amphiphilic means like having both characteristic as far as I can relate to the word that's told. Having both the groups. Like surfactants are amphiphilic because
A molecule having both hydrophobic, nonpolar, and hydrophilic polar regions.
okay. So
Yes,
so amphiphilic is having
both the
like
groups.
surfactants are both na. In that you are
Uh,
having hydrophobic tail and hydrophilic head.
yes, sir.
So I think that is clear now. So this you see explain the continuum of hypothesis. and its validity. So you know that it is valid for the Knudsen number. There is a range of Knudsen number that Sir has talked about, and that particular slide was a bit more explanatory. Like this, there the entire range has been shown for the validity of this. This is visible.
Hmm.
Okay, this one. You see, Knudsen number. First of all, it is the ratio of the mean free path. What
Mean
is
free
mean free
path.
path?
Mean free path is the distance traveled by a molecule between two collisions.
Successive collision.
As of two successive collisions. Huh?
So, what do you actually feel about this? If a molecule is there, suppose water is there. So, have you ever thought of that two water molecule is moving in your bottle, and then is there any is there any this mean free path associated?
Like it is so small that we cannot see with our naked eye, but yeah, like two particles are
Hmm.
interacting in such a manner that after one collision, uh, I mean between two collisions, I mean one strike it strikes and then it strikes with again particles. The distance it travels,
Hmm.
that one first particle, the distance it travels is the mean free path. It will be very small compared to the physical dimension
And
which
again and
the
again
bottle is kept.
again and again this water you are assuming that molecule to be a spherical one, but essentially in the water there will be two hydrogen and one oxygen, and they will be in the angular shape. So
Hmm.
collision between two hydrogen, one oxygen, and the collision between one oxygen, the second oxygen, like that.
Hmm.
So there could be different. I have read one paper once. So they have talked about the orientation and the relation of the successive collision, uh, mean free path to the orientation of the molecule. I exactly didn't remember, but it is there. So that
So like in that, like in water, three atoms
uh,
are
so
there,
so
two
so so
hydrogen,
in that
one.
they have considered the effect of that also. So
Okay.
otherwise, we don't like in the class ninth
Uh,
also kinetic theory of gases we used to read it,
yes, sir.
but that time it doesn't make sense. Okay,
Sure.
so here the Knudsen number came into the picture, and we got the information that below 0.01 Knudsen number, the fluid will be considered to be continuum, and
Hmm.
other is the these are the ranges. So the last question that is there, this one, flow can be considered as sleep flow for. So you this is directly from this particular slide. So sleep flow is between 10 to the power minus 2 to zero
Yeah.
point 0.1. Okay,
Yeah.
so this is the correct one. So how much time we are having still?
I think it was still five, no?
So it's around completed, so I will have to
Uh,
anyway cover it. So C. Okay, so this what is Suratman number?
which number?
This Suratman number, it was there in the third lecture.
I haven't gone through
You
that.
haven't gone through, so let me just release that. It is there, and like last third or fourth slide, sir was explaining about this in the regimes. Do you know the regimes?
Yes, sir, that I covered.
You covered that. Na? This there, sir told about this particular raise the concept related to this is nothing but like a Reynolds number, a factor that actually explains the ranges for the different regimes. Let me reach there, it will be much easier for me to explain there. This is 12th lecture where I reached. This is 10 flow regimes. What is so where is that? Yes, this one. Now you see, they in the concept of microgravity, sir told that Suratman number is the ratio of the Reynolds number to the capillary number.
Yes, sir.
Okay, this you know that capillary number is Weber number to the Reynolds number.
Hmm. That I know.
So with that it becomes like Reynolds number to square divided by Weber number is the Surtman number.
Certainly.
So this Surtman number is like liquid Reynolds number based on capillary number. So liquid Reynolds number based on capillary number is the Surtman number, and this you just see this is Surtman number equals to Reynolds number divided by capillary number. Now everything will be relatable with that. And which one of the following is not very important in the microgravity flow regime? So this microgravity flow regime, in that what is important, what is not important. This one you see 16 slide here. Here you see this in the case of microgravity, this gas and the liquid Reynolds number and the capillary number and the Weber number,
Mhm.
these will be important. And this density ratio, if two fluids are there, suppose oil and water, so viscosity of oil to the viscosity of water will be having not much effect. So what are not important? So D and E are the correct answer here. D and E. This has been taken directly from the slide. You see this one.
Yes, I haven't covered this.
Okay, no problem. So actually, when you cover it, then it will be relatable. So no issues.
Yes,
That's
sir.
why these lectures are recorded one. So gas liquid sleep is given by bubble rise velocity. Is it right or wrong? Gas liquid sleep is given by bubble rise velocity. So there is a gas liquid sleep. It is again from a slide. There the difference between the the gas velocity and the liquid velocity. Here you see uh, the gas liquid sleep given by the bubble rise velocity, and the bubble rise velocity is what? Ug, gas velocity minus liquid velocity. So this bubble rise velocity is gas velocity minus liquid velocity. So this is the gas liquid sleep is given by bubble rise velocity. It is correct. True. Okay.
Okay.
Which of the following relation is not for the surface tension and the temperature? So this is effect of surface tension, temperature on the
Uh,
surface tension.
It was relation is there. Katawama relation, I think also he talked about. But Guggenheim.
So you see, it is there. All the four are there.
Hmm.
Okay, all the four are there. This Katama and Guggenheim, these are together.
Huh.
So like at the critical temperature, you know that the surface tension is zero.
Yes,
What is critical temperature? Just for the sake of your information, I kept.
critical temperature is that temperature at which this
all the
only the all vapor phase exist
all the
and no
three
one.
phases exist. Okay,
No, only the vapor phase
in the critical, and at the triple point temperature it
at
exists.
triple point.
In the critical temperature only vapor phase exists. Okay,
Yes,
so uh, only vapor phase exists.
exist.
Okay, TC is the critical one. Okay, surface tension always decreases with temperature. Is it correct?
Yes,
Mm, it is correct. So true. And about Marangoni, you know something? Marangoni convection explains its key feature. What is this?
Marangoni. I think he explained in that uh, due to the temperature difference, there will be some. Uh,
Okay, you think about this.
at the
Yes,
interface
at the interface.
this happens.
Okay, so for example, there is a interface of two fluids. Okay, and
Yes,
so if there is interface, there will be surface tension interfacial tension gamma 1 2,
Hmm.
and this interfacial tension which is gamma 1 2, it is there. This will be function of temperature.
Yes, sir.
So in the Marangoni convection, if the surface tension will be the function of temperature, and
Hmm.
when this surface tension will be function of temperature, then there will be an instability coming up into the fluid. So there will be a flow structure coming up. So this, you see the Marangoni convection, which is caused by the gradient in the surface tension.
Hmm.
So gradient in the surface tension will be there, and this gradient in the surface tension will be getting related with the
Convection.
wait, let me tell you, this normal balance and the tangential balance is there now, and this was
Hmm.
there at the interface.
Yes,
And
sir.
this at the interface, whatever normal the tangential balances you will be having in terms of the continuity equation and the Navier-Stokes equation. To solve the continuity and the Navier-Stokes equation, only you are having boundary conditions.
Hmm.
To solve any partial differential equation,
Any.
and
Hmm.
these boundary conditions will be then which these boundary conditions will involve the gradient of surface tension. There will be terms coming up, del gamma by del t into gradient of t in the tangential valence and the in the normal valence. This kind of terms will be coming up, and this term is coming only because your surface tension is changing with the temperature. Spatial
Hmm.
variation of surface tension with the temperature, and that's the Marangoni convection. So
Convection.
here if you see, this is the normal valence I wrote here also. The dynamic conditions that was there. Dynamic condition, why dynamic? Because that interface is fluctuating. So there will be pressure and the viscous stresses are in the equilibrium with the force due to the surface tension. So see the first two term is minus P2 plus P1 is the pressure valence, plus eta
Hmm.
tau 2 minus tau 1. So this n dot tau 2 minus tau 1 is taking care of this tau is mu du by dy. So this is the viscous stress. So this pressure and the viscous stress is getting balanced by the force due to surface tension, which is gamma into curvature. Surface tension into curvature. So this
Yes.
and in this case, if you see here, if this Marangoni effect will be there, then this Marangoni effect will involve the gradient of the surface tension with the temperature, and that will be reflected in the normal and the tangential valence for your flow system. So this will be, you just look at there in the lecture, sir has explained it a bit more.
Hmm.
And then the very basic question, like what is the difference between surface and what is the difference surface and the interface. So just some words that you can tell about interface.
Interface is like between two fluids
Yes.
or two, yeah, and the surface when we talk about it can be of a single fluid itself. When we derive this equations, we take a surface and from that surface we talk about that this traction force vector, and like in of a particular fluid only if you're talking
In
about, then
it
we
means
can
in
talk
the
about
interface there will be two
two.
distinct phases. Two distinct
Hmm.
phases will be there in the interface. But in the surface, for the surface, there can be single distinct phase. That surface can be used for example, two distinct phases means between oil and the air. There will be interface now.
Yes, sir.
So oil will be one phase, which is the distinct phase, and air is the another phase. And these are this one you see discuss the different dimensionless numbers. So the bond number, capillary number, and Weber number we have discussed
Hmm.
these numbers. So this is there, and this what is the electrokinetic effects. This lecture have you gone through? In I think second lecture it is there. the electrical double layer, electrophoresis, electroosmosis, stripping
No,
potential, and the
Abhi, I
sedimentation
haven't
potential.
gone through this. It didn't come up, Abhi.
Anyway,
I went through lecture 2, it's
no,
out
it is
there.
in the lecture one last, I think. As far as I remember, it is in the lecture one, last few slides. It is there. So these definitions you have to be very clear with. Lecture one, last slide, I think. No, no, no. So he's you see the interface is the macroscopic view,
Hmm.
and the interface in the microscopic view. So two distinct phases are there, and
Like if there's the same fluid and one is vapor, one is liquid, then also there will be an
yes,
interface,
there
right?
will be interface. So yeah, here you see in the first lecture, lecture number one, you see this is lecture two, lecture one. You are having this electrokinetic effects. In this, you are having this electroosmosis, electrophoresis, and then streaming potential and the sedimentary potential. So electro means in the both you are having applied electric field, and under that how your surface charge, stationary surface charge is moving in the liquid, or how charge surface is related to the stationary liquid. In that terms, these definitions are defined. And in the case of streaming potential, the electric potential induced when a containing liquid uh, uh, flows along a stationary charge surface. So based on that, there will be induction of the charge. And again, in all these, the role of dipole, induced dipole, and those things will be
Predominant.
predominant, and that will be added up. So if you are having external electric field, those effects will not be very much dominant, because electric field you are controlling externally, and that is anyway will be much higher than those microscopic forces. So this I
Okay.
have explained why mixing is an issue in the microfluidic channel. And this continuum is explained. Which effect are dominant in the multiphase microfluidics? Small diffusion, this one is clear na. Small diffusion effect, surface dominating effect, non-continuum effect, low Reynolds number effect.
It's
I
four.
think all the four are correct.
Hmm.
A, B, C, and D is the correct one here. And in this one, what are the factors that are dependent on the surface dominated effects?
Surface dominant. This first one will be their surface area to volume ratio, friction, viscous effects, hydrostatic effects, height, and
So so
for CIM, no, I think all will be there.
this
C,
A, B, C, D. All will be correct answer. This is directly from the
from the notes.
discussion also explained. This one is explained through the video also. I think mixing issue in the microfluidic channel, and this Weber number and this capillary number and the Weber number, we know viscous force to the surface tension force, and inertia force to the surface tension force. So what is bond number? Only that is left, I think.
Bond. I'm not sure on bond number. I think sir has explained though, but I'm not able to recall this.
So this bond number is here, buoyancy to the surface tension force. So buoyancy is delta rho GD. So if gas liquid is there, and those gas liquid in the horizontal channel, so there will be stratification, and there will be change in rho 2 minus rho 1 density will be coming up. So bond number takes care of the buoyancy to the surface tension, and this capillary number takes care of viscous force to the surface tension, and Weber number takes care of inertia force to the surface tension. So
Surface
so
tension.
everywhere you are having surface tension to be at the denominator, and
Hmm.
accordingly different forces like gravity force, viscous force, and the inertia is at the numerator in the bond number, capillary number, and the Weber number respectively. So this is explained. I think I am done with all the questions. How many questions were there? 35. Okay. So thank you so much. Your name, please.
Taha, Sayyid Taha.
Okay. Thank you so much for your patience. It's been like more than
Thank
2 hours.
you.
Yeah. Thank you.
This was a helpful session. Thank you
Thank
so
you so
much.
much. Yeah.
Okay.
You can exit the meeting.
Okay, sir.
Thank you.